Good afternoon, everyone. So today's session would be about modular arithmetic. So let's start. So what basically is modular arithmetic? So modular arithmetic is a system where numbers wrap around a certain value, and this is basically modulus. So in simple words, after applying modulus of m on any numbers, the result between the result will be in the range of 0 to m minus 1. So let's see with the help of an example. So here I've taken 100 modulo 25, which is basically 0, and 37 modulo 7 is basically 2. So what exactly is modulo? So modulo is basically remainder, the number which remains after dividing by the denominator, the number which remains. So basically this is modulo. So if we modulo by 1000, so what exactly we get is the last 3 digits, 2, 3, 5. So this exactly is modulo. So when I said that modular arithmetic is a system where the numbers wrap around a certain value, so let's see what it means. Okay, so here I have done 1 modulo 3, 2 modulo 3, 3 modulo 3, 4 modulo 3, similarly up to 10. So let's see what happens. So 1 modulo 3 is 1. Why? Because when you divide 1 by 3, the value which is remained is 1. So that's why 1 modulo 3 is 1. Similarly, 2 modulo 3 is 2, because when you divide 2 by 3, it's not completely divisible, and the value which is remained is 2. 3 is completely divisible by 3. So hence, the value which is remained after division is 0. Nothing is left. It's completely divisible. Similarly for 4, 5, 6, 7, 8, 9. As you can see, the pattern repeats. 1, 2, 0, 0, 1, 2, 0, 1, 2. So, the result is in the range, indeed in the range of 0 to m minus 1, wherein our m is 3. So, this is basically what modulo is. It is nothing but the remainder of a value when it is divided by m. So, why is it used? Modular arithmetic is commonly used to limit the integer value. So we know that in C++ and various other languages, there is a limit to the integer. So in C++, integer has the following limit, long has the following limit. So in order to keep the values within a bound, we use modulo. So here are some of the properties of modular arithmetic. A plus b mod m is a mod m plus b mod m mod m. A minus b mod m is a mod m minus b mod m mod m. And a multiplied by b mod m is a mod m into b mod m mod m. So these are the 3 properties of modular arithmetic. So where exactly it is used? So if you are new to the world of competitive programming, or if you have done CP, DSE or something like that, you must have seen that sometimes in some combinatorial or probability tasks, they ask, the output is a huge number, very huge number. Suppose they ask you to calculate 20 factorial, and 20 factorial is a very huge number that can't be stored even in long. It can't be stored even in long. So what they ask you to do is to output it modulo 10 to the power 9 plus 7. So when the output is very huge, they ask you to output it as the modulo of 10 to the power 9 plus 7. So let's do a factorial question, as I said, like 20 factorial, to understand the multiplicative modulo. So let me start. I'll go on id.new. So get C++ id. So if I had to calculate the factorial of a number, say 10, so what I would do is int fact, okay, let me take long fact is equals to 1 and apply a for loop. Then what I do is fact is equals to fact into 1 into I, alright, and see out the factorial of n is factorial of n is fact. Alright, so let's run it and see what we get as an output. Okay. I don't know. Okay. Okay. So here we got the output that the factorial of 10 is 362888800. Okay, fine. It's well within the limits. All right. So now what I do is run it for 15. All right. Okay, we got that. Okay. Let's get this cleared. Okay, the factorial of 15 is still within the limits. Let's try about 20. And when we try to calculate the factorial of 20, as you can see, what we get is a very garbage value. It has no significance. So this is the exact reason why we use modulo. So when the number is very huge and it exceeds the integer limit of the C++ integer, the compiler behaves abnormally and just produces some random value. So this is where we use modulo. So the problem statement says that output the number as modulo 10 to the power 9 plus 7. So what I basically do is take int is equals to m is equals to say I9 plus 7 and just do a simple thing, right? Alright, just bound this by a modulo m. Alright, and now our code will work fine. Okay, there's still some issues. Okay. Okay, the code was successfully executed and the factorial of 20 is 1463263. So well, the factorial of 20 is not exactly this value, but when you modulo the factorial of 20 by this term, this is what you get. So this is what modulo is. So this is what modulo is, just to give you a gist. And as we saw this properties that a plus b modulo m is this, a minus b mod m is this, a multiplied by b mod m is this. But what about division? Why is there no division formula? So the reason is that this formula a divided by b mod m is not a mod m divided by b mod m mod m. This is wrong. So what is the right formula then? The right formula is a divided by b mod m, a mod m multiplied by b inverse mod m. So what basically we have done is switched from division to multiplication and applied this formula. So how do we got from b to b inverse? So we take this idea from arithmetic. So when we are asked to perform a divided by b, so is it the same thing as a multiplied by b inverse? Well, yes. So this is where the idea of the inverse originates. So what exactly is b inverse here? B inverse mod m. So this is exactly what today's session is about. It is about modulo multiplicative inverse, wherein instead of dividing by b and then performing a module, wherein in a task where you have to divide by b, a denominator, and then perform mod m, so you switch it, you multiply by the modulo multiplicative inverse of b, multiply it, and then find a mod m. So this is what today's session is about. B inverse, that is modulo multiplicative inverse. So we'll understand that where exactly it is used, how it is used, and why it is used. So we have covered why it is used. It is mainly to wrap around values in a certain theme, in a certain range. So this is why it is used, and where it is used. So let us have a look at this problem, binomial coefficients on CSS problem set. Binomial coefficient is nothing but like a factorial, something of your sort, like NCR, NPR, whatever we used to do it during JE days. So this is the simple formula: a factorial divided by b factorial multiplied by a minus b factorial. So it would be really great if you guys can try this problem, you know, and try to get your like a accepted solution, so that we can, you know, see where we are going wrong and why do we use modulo multiplicative inverse. So basically it's nothing but like problem set task 1079. You guys can try this problem. Just have a look at the problem statement, try to come up with a code, try to apply what you think is correct. So as you can see, they have said us like, you know, your task is to calculate n binomial coefficients modulo 10 to the power 9 plus 7, and they have defined binomial coefficient, and we assume that a and b are integers. You guys can try this problem for a couple of minutes, and let's just discuss the problem and see why it is used. So in the meanwhile, I'll also try to do this problem with you and see where it goes wrong. So So I'm taking const int m. Okay, so I realized I was silent for a long time. Okay, so here's some solution that I've come up with. So it's like a lot of you must have done what I show. So first of all, constant m is equals to 10 to the power 9 plus 7, and then I just pre-computed the factorial values because I didn't want to calculate it again and again. So this is how I went about the pre-computation of factorial. So I took n is equals to I6 because the range of a and b were among I6, so I'll take it like I6 plus 5 is okay. So then I set the array as int factorial n. I set the numerator and denominator, and then I pre-computed the factorial values till the value of 5. So as you can see is like basically factorial also follows the substructure problem that factorial of number I is basically number I multiplied by the factorial of the number previous to it. So this is what I have done. So like to calculate the factorial of I have multiplied I by the factorial of the previous number and then just taken a modulo m. So this is basically what I've done, and so then I take the input a and b. Okay, so there are test cases in this. Okay, fine. So I'll just okay, so int t, c int t, while t minus minus, right? So yeah, cool. So for the test cases, different test cases I've taken this, and while t minus minus int a b, c in a b, and this the numerator is numerator. Okay, fine. Numerator is factorial of a, the denominator is factorial of b multiplied by factorial of a minus b mod m. Okay, so this is my numerator and denominator. So what my output should be is like numerator divided by denominator. Good. Okay, let's just test this. Alright. So custom input, provided the input, run. Okay, alright, where is the error? Alright, no problem. Okay, fine. Okay, I forgot to give. Okay, so as you can see, my output is 10, 8 and 1 to 6, which matches the required output, which is 10, 8 and 1 to 6. And so the expected output is, so the output that I got is 10, 8 and 1 to 6, and the expected output is 10, 8 and 1 to 6. So let's just try to run this code. So okay, login to continue. Okay, so okay, I'll just transfer this code to CodeChef and download it. Dude, CodeChef slash ID. Okay, alright, nice. C++ 17, cool, pretty cool. Alright, we'll just run this once again to show you that it does really work. This solution works for the test case. It's a proper solution but won't pass. Let's see why. Oh no. Okay, alright, no problem. It works fine. Just download it, id.cpp. Okay, I need to also log in on my CSS. So okay, alright, I've logged in on my CSS and let's try submitting this code. And as you saw that it works fine for the sample test case, and let's see does it pass or not. Alright, so it's a wrong answer. It just got accepted for one test case and it just gave wrong for everything else. So what's the reason? User output this, the correct output is this. So the reason is that this actually what we are doing is wrong. Oh no. Oops. Okay. So as I said earlier that you can't do this. A modulo m divided by b modulo m. This is not exactly the same thing. You can't do this. And this is exactly what we have been doing. If you can see that we are doing like we're finding the numerator, then we find a denominator, and then we divide it, and then modulo m. This is not right. So we need to convert this division into a multiplication, and we need to convert this division into a multiplication, and the multiplication should be a b inverse. So how exactly do you find b inverse? So what exactly is b inverse? So as you can see, so in normal arithmetic, a into b is equals to 1. Alright, so if a is 5 and we want that 5 into some value b should be 1, so what should be 5? What should be b? It should be 1 by 5. So 5 into 1 by 5, it will give us 1. So can we say that 5 is the multiplicative inverse of 1 by 5 and 1 by 5 is the multiplicative inverse of 5? This is true. But when it comes to modular arithmetic, we don't need that, like, a into b should be 1. The only thing that we need is that a into b mod m should be 1. You don't need a into b is equals to 1. You just need a into b mod m should be 1. So let's see what I mean by example. So suppose that my m is equals to 7. Alright, m is equals to 7. Alright, and my a is equals to 5. Alright, so what are the condition? A into b mod m should be equal to 1. Should be equal to 1. So if I write it again, so 5 into b mod 7 should be equal to 1. So what can I take as b? Can I take b as 3? Yes, I can, because 5 into 3 is equals to 14, and 14 mod 7. Okay, alright. Wait a second. Where did I go wrong? 5 into 3. Okay, alright. 5 into 3 is 15. Oh my god. 5 into 3 is 15, and mod 7, it gives me 1. Alright. So as we can see here that this thing is satisfied by a is equals to 5, b is equals to 3, and m is equals to 7. So when m is 7, 5 and 3 are multiplicative modulo inverse of each other. So whenever they ask you to divide by 5 and perform modulo operation, you can instead multiply by 3 and perform the operation. So let's take an example, like, okay, let's take that 60 let me show you a quick example, like 60 divided by 5 modulo mod 7. What is it? 12 mod 7 is equals to 5. Alright, and since since 3 is the multiplicative modulo inverse of 5, instead of dividing by 5, multiplying by 3 should also give you the same result. So 60 into 3 mod 7 is equals to 180 mod 7, which is, it should be 5, but let's just like take a calculator and confirm it. Like, okay, let me go here. Alright, and just see out 180 mod 7. Alright, but okay, is 175 divisible by 7? Okay, yeah, 170 is divisible by 7. Okay, they are again asking, so 174, it should be again 5, and I can prove it, like, because 175 divided by is divisible by 7, because 7 15s are 175, so of course 180 mod 7 should be 5, and yeah, this is true. So when I say that, for this case, when m is equals to 7, a is equals to 5 and b is equal to 3 are modulo inverse of each other. So instead of dividing by 5, multiplying by 3 will give me the same result. And likewise, whenever we are asked to divide by 3, we can multiply by 5 and we will still have the same result. So this is basically modulo multiplicative inverse. So this is the main difference between the modulo inverse. Alright, so I'll close the word file. So how do you exactly find this multiplicative modulo inverse? So for the first step is brute force approach. So all we know is that we just need that a into b mod m should be 1. So we can also expand this as a mod m into b mod m is 1, as we have seen in this property right here. So from here we can infer that there is no point in taking a value bigger than m, because anyways these values, the value of these these values will be reduced down to the range 0 to m minus 1. So we can take the inference that b lies between 0 to m minus 1, and we can simply run a for loop, and check that whether a into this value gives us, and mod m gives us 1. So like if we had to, like, for a is equals to 5 and m is equals to 7, we had to find the modulo inverse by a brute force method. We would first do 5 into 1 mod 7, 5 into 2 mod 7, 5 into 3 mod 7, 5 into 4 mod 7, and whenever a value gives us mod m is equals to 1, that would be our multiplicative modulo inverse. So this is the brute force, and the efficient way to find the multiplicative modulo inverse of a number is through Fermat's little theorem. So what Fermat's little theorem states that if m is a prime number, then for any integer a power m minus a is the integer multiple of m. So this is the mathematics. You can, like, just ignore it. There's no need to understand it, but it's better if you understand it. So a power m minus a is mod m, so which can also be represented as like a power m mod m is a mod m, and the condition to sum it up again is that the GCD of a and m should be 1. A and m should not be divisible by each other, and m should be prime. So this is what Fermat's little theorem states that, and we'll manipulate this theorem into what we need, modulo inverse. Alright, so what I do first is divide both the sides by a. So if just see the right side, so a power m mod m is a mod m, then I divide both sides by a. So a m minus 1 mod m is 1, and then I multiply both sides by a inverse, alright, which is the same thing as divide by a. So what I get is this thing. So when I divide the above formula by, multiply with the above formula by A inverse, I get this. A power m minus 2 mod m is equals to A inverse. Alright. So this is the required formula to find the A inverse. Alright. So what A inverse basically is, so whenever they give you a number x and a prime number m, the multiplicative modulo inverse of x will be x inverse x power m minus 2 mod m. So this is the only thing, you know. So this is what multiplicative modulo inverse of any number is. So whenever you have m as prime and they give you a value x, so this is what its multiplicative modulo inverse will be. So in order to, so now let's see how we can use this formula to solve our today's problem. Alright, we'll use this thing. Wait a second. Alright, so the step 1 would be to calculate the numerator mod m and the denominator mod m. You know what we do. Alright, so a numerator is a factorial and a denominator is b factorial into a minus b factorial. Alright, so what we need to do is basically calculate the numerator mod m and the denominator mod m. So which is what we do here. Wait a second. So alright, so this is what exactly we do. Numerator, since these factorial values are in terms of mod m, so we find the numerator in terms of mod m and the denominator in terms of mod m. So basically a numerator is a factorial, the numerator is factorial of a, and the denominator is b factorial multiplied by a minus b. So our denominator is b multiplied by a minus b factorial, which modulo m. So the first step is done. The second step, instead of dividing, so what exactly we do is this thing. Alright, we divide a by b and then calculate a mod m, which is wrong. So what we should do is, you know, multiply by the b inverse, multiply by the denominator inverse. So the second step is calculating the denominator inverse. Alright, so the second step would be to calculate the denominator inverse. So how do we calculate the denominator inverse? By using this formula. Alright, so denominator inverse would be denominator power m minus 2 mod m. Alright, so how do we do that? So we need to do, so we can run a simple for loop to, so our second step, step 2, is to calculate denominator power m minus 2 mod m. So we can do this using a simple for loop, nothing drastic. Oh no, since our m is to the power 10 to the power 9, we need to use binary exponentiation. I'm not sure if I'm pretty sure that you must be aware of binary exponentiation. So I'm just going to copy paste the binary exponentiation code. So to not elongate the session, I'll just take the function which is available right here. Sweet. I'm just gonna paste it. So basically what binary exponentiation does is it gives you a power m mod m, but basically that's what, basically it just gives you the binary exponentiation. Like, you know, if you have to calculate a power n, and if you run a loop n times, it would take O of n times. So what binary exponentiation does is calculate a power n in log n time. So instead of O of n, we do it in log n time. Alright, so I've just pasted the code, no biggie, and then we calculate our denominator inverse. Alright, is it long? Okay, it's long, no problem. Okay, it's fine. In denominator is equals, okay, inverse denominator is equals to bin power what are the terms that we need to pass is denominator m minus 2, alright, and the m, right? So we get the inverse denominator, and then it's just that we, instead of dividing by denominator, I've just I just commented out. Wait a second. Alright, so instead of dividing by denominator, I'll just multiply it. I'll take a 1 LL also in order to, like, not run into any sort of memory issues, something like that. So inverse of denominator, and this should work fine. Let's hope that it works fine. Alright. Yes, 10, 8, 1 to 6. And I hope this code passes. It will pass definitely. Let's try. I'll download it again and submit it on CCS. Where is CCS? Okay. Testing time. Okay, give me. Okay, so let's go. It's been accepted in one go. Very nice. So I hope so our problem is solved. So basically what the steps we have done is, basically instead of dividing it by, instead of a divided by b, we have just multiplied it by its inverse. So this is the only replacement, and what we have learned today is calculating the inverse thing. And how do you calculate inverse thing? It's very easy. Just ensure it's very easy. It's just one line. X inverse is just x power m minus 2 mod m. So whenever you get a problem where you have to divide a certain value, so what the only thing we have changed is, earlier we were doing this. We are dividing it and then performing the modulo operation. But now what we have done, we have only calculated the inverse denominator, modulo inverse of the denominator. By doing this, we have raised the denominator to the power of m minus 2, and while maintaining that this huge number lies in the range of mod m. So I have passed these three parameters, a, b and m. So denominator power m minus 2 m. So this will give you the inverse denominator, and instead of dividing by the denominator, just multiply by the inverse denominator and calculate m. So it's as simple as that. So I hope you took something from this session. That's all from my side. I thank you for attending this session, and thanks for your time. So I'll please do solve this problem, binary exponentiation. A lot of companies just ask it, like, because it's a very easy topic, and it's a very good topic to know. If you are interested, I can show you a couple of Code Forces blog where you can solve some questions. Code Forces modulo. So there's this blog, modulo arithmetic for beginners, which has some questions at the bottom. You can solve these questions if you want, and you can definitely solve the CSCS problem, binomial coefficient. And to talk about recent problems in Code Forces, recently there was a problem in a diff 2 contest. It was a C problem on Code Forces just recently, couple of weeks back. I'll just give you the link to that problem. And card games, I'm not sure it was called card games. Yeah, card games. Yes. So this is a 1500 problem in Code Forces, but it's not that difficult. If you understood today's session, you would be very easily you will solve this problem. Please do try this problem, and please do solve the binomial coefficient problem. I think you will be good. All the best. Thank you. exit.